Hello and welcome to the SIMPLIS Technologies APEC 2021 vendor seminar. My name is Andreas Stupar. My colleague Matthew Fortin and I will be presenting some new features for SIMmetrix SIMPLIS version 8.5. I will be presenting some enhancements to the SIMPLIS Magnetics Design Module, or MDM for short. And then I will hand it over to Matt, who will talk about the parameter editing GUI tool and the triggered oscilloscope plotting function. The main new capability in MDM for 8.5 is the ability to more precisely control how transformer winding turns and magnetic core air gaps are placed, and we will go over some examples demonstrating this. So first, arbitrary transformer winding turn placement. In 8.5, scripting-based winding placement now allows for the precise placement of each and every turn via XY coordinates. So you can achieve transformer winding arrangement as pictured here, which were not previously implementable. The arrangements that are made possible or easier to implement in 8.5 with this new ability are split bobbins, layer-by-layer interleaved windings, turn-by-turn interleaved or so-called bifilar wound windings, split windings, planar transformers, and so on and so forth. So let's take a look at how this works. This is our standard self-oscillating flyback converter example with an MDM transformer that you can find in our example directory when you install the program. And when we take a look at the transformer design here, we can see that this is the standard simple placement that was available in 8.4, where we have first the primary winding and then the first secondary and the second secondary, all from the center leg outwards. But now if I change the placement method from simple here to scripting, I have now a box to write a winding placement script, which is done in JavaScript, and there is a function called setConductor, which controls how the turns are placed. So here inside of a loop, we are placing 9 turns of the primary winding. So for example, if I change this to 2 and then I click apply, I have now spread the turns more along the bobbin. And of course, I can place, for example, a single turn of the first secondary winding. So if we set the XY coordinates, and now we've changed the ID of the winding to say that it's the next one, click apply, and now we have a turn of the secondary. Let's take a look at a model that I've prepared that makes use of this new functionality. And what we have here now is modeled is a planar transformer. This is a planar ELP64 core, and we are modeling the fact that it is sandwiching a PCB board, so where the PCB traces are being used to create the windings. So if we zoom here, we can see here that we have a primary winding where we are using square conductors, so it's several turns, several traces within the same PCB layer, and then there are 2 layers. For the first secondary, we are using 1 turn per PCB layer, but with a via here we can make them bifilar, and here we have just a single turn per PCB layer, secondary 2. And if we click finish here, it will be written into the circuit and ready for simulation. This simulation, due to the large number of rectangular windings, will take quite some time, so I've already prepared the result to show you. And if we were to run the simulation, this is the result that we would get. Very low core losses in this case. Winding losses are about 0.457 watts, and they are broken down by type. We can see the core temperature and the winding temperature. We have the total boxed volume of this transformer, the magnetizing inductance and the leakage inductance. and we can take a look at the losses by winding here. And if we zoom in here close to the air gap, we can see how here we see the effects of the proximity loss generated by the proximity field, the fringing field of the air gap. And in these edges of the PCB traces, which are close to the air gap, we can see this red color, meaning that the losses are higher due to the proximity effect. And of course, as before, we have the waveforms here, the L versus current characteristic of this transformer, and the details of the transformer design in the last tab. So as we saw, the first example we saw using this new turn placing capability was the planar transformer. And the second example will be an LLC converter, where we want to create a LLC power transformer with a purposefully high leakage inductance in order to remove the need for a discrete resonant inductor. So we want to go from this type of structure where we have a discrete resonant inductor, LR, and a power transformer, to a structure where it's all just the power transformer and it's the leakage of the transformer which is creating the resonant inductance. So let's take a look at the circuit here. This is one of our LLC examples. It is a detailed model of an Infinio demo board that we covered in a webinar last year. And if you zoom in here to the magnetics, you will see that we have a discrete resonant inductor. It's about 14 microhenry. And we have a transformer which has a magnetizing inductance of about 180 microhenry. And if we take a look at this design, we can see that it's a very nice compact design on a PQ core with interleaved windings and is designed to have minimal leakage. So if we take a look at the leakage, actually, we will see that the leakage is only about 1.7 microhenry. But as we said, now we want to go to a structure like this, where we have removed the resonant inductor and everything is now integrated here. So if we open here this transformer, we will see that a winding script has been created, a winding placement script, such that we put the 4 layers of the primary winding all the way at the top of the core, and here we have the 2 secondaries all the way at the bottom of the core. So in reality, you would implement this with some kind of split bobbin, or maybe there would be here some kind of block of plastic that is separating the windings, and of course here you would need tape to get the distance between the layers. But this allows us to purposefully create a very high leakage, and we are doing it with the same PQ core as I was showing previously. So if we now simulate this design, I can show you just that this is the same LLC converter, just with the discrete resonant inductor missing. And if we run the simulation, here we see the waveforms of the LLC converter. And here we have the MDM transformer analysis results. And we see that we have 183 microhenry magnetizing inductance and about 11.3 microhenry leakage inductance. We can, of course, take a look at the losses by winding again as before. But we can see here that now on this PQ core, we have integrated both of our magnetic devices essentially and saved quite a bit of space by removing that resonant inductor from the board. So as we can now place transformer winding turns using scripting, we can also place air gaps for 2 types of core shapes using scripting. One is the UU scriptable air gap core, which is available for inductors only and is shown here. And the other is the EE scriptable air gap core, which is available for inductors and transformers. So you can see here how we have 4 air gaps on each leg of this UU core, but these gaps here are larger than these gaps here. So let's again take a look at an example in SIMPLIS. This is our standard buck converter example with an MDM inductor. And if we open it here, now let's load an inductor design which uses the scripted gaps. And you can see here how we now have on this E-core several air gaps, 1, 2, 3, 4, 5 on each of the 3 legs, and they have been placed using this script here. So again, there is a single script function where we specify on which of the legs the air gap should go, what is its size, and what is its position. So we can demonstrate here adding a new air gap. Let's say we want to have this one only on the center. We can have it the same gap size as the previous ones, and let's put in a position here, click apply. Sorry, that was misspelled. And there it is. And now we have an extra air gap here. And if we simulate this, we can now see, again, the loss breakdown for this inductor. And if we take a look at the losses by winding, we can see how the turns which are far away from the air gaps have a lower loss density than the ones which are close. They are red. And that is, again, due to the proximity fields of all of these air gaps, which MDM is calculating correctly. So this completes the overview of the new MDM features in 8.5, and now I will hand it over to Matt Fortin.
Thank you, Andrea. As stated at the beginning of this presentation, I will be covering 2 new features of SIMPLIS SIMPLIS version 8.5, the parameter editing GUI tool and the triggered oscilloscope plotting function. Parameter editing dialogues have been included in SIMPLIS SIMPLIS for many years. However, to add one, you had to use a third-party spreadsheet software. In version 8.5, the dialog creation spreadsheet is now incorporated within the symbol editor. Since an external program is no longer needed and there is no copying and pasting necessary, the ease and speed of developing a dialog has been greatly increased. For this example, I will use a subcomponent that already has a tab value dialog defined and will modify its layout. This tool can be accessed from the symbol editor by using the property/pin add/edit parameter editing dialog menu item. For those familiar with using the spreadsheet, this process should be very familiar. These 5 steps will walk you through all aspects of the parameter editing dialog, the type of dialog, the tabs, the groups within the tabs, the parameters within each group, and finally, the title of the dialog. A major improvement from the spreadsheet process is the addition of a way to preview the dialog. Pressing the Preview Dialog button will display how the dialog will appear with the given properties. Previously, you had to go through the entire creation process before you could view the dialog. Now, as you may notice, there are a few inputs that don't necessarily make sense, like the filter gain being a drop-down menu, and the resistor value being an integer value. With this tool, I can easily change these input types without ever leaving the symbol editor, let alone the SIMPLIS SIMPLIS environment. To change these input types, I will navigate to step number 4 and change both the resistor value and filter gain control types to be real. I will also remove the range of the filter gain as it is no longer needed. Now I can quickly verify my changes by selecting the Preview Dialog button. As you can see, my filter gain is no longer a drop-down, and my resistor value is no longer an integer. The last item to be covered in this presentation is the triggered oscilloscope plotting function. This function will overlay multiple segments of a curve to produce a waveform similar to an oscilloscope trace. This will allow easy comparisons between sections of periodic signals. In this example, I am investigating the output voltage of a digitally controlled synchronous buck converter in red being subjected to a periodic load pulse in blue. To execute the triggered oscope plot, I will use the Plot Oscope View menu item. In the first section, I will choose which waveforms I would like to overlay, in this case, Vout. Second section will determine my trigger waveform, iLoad. Next, I will set the trigger level and trigger slope. Since my trigger is the iLoad current, I want to choose somewhere between the 10 amp and 1 amp level, so I'm going to choose in the middle at 5. And I'm curious about the low to high load step Vout behavior, so I will choose the positive trigger slope. Finally, I will set on which interval to view the data. In this case, I want to see the first 100 microseconds after the low to high load step. So I'll change this to 100 micro, press OK. Now, because this is a digitally controlled converter, it is easy to see the discretization within the feedback loop. This concludes our vendor seminar presentation. If you are interested in any additional information on today's topic, or for information on joining us at our virtual booth, please visit simplis.com. On behalf of Andrea and the rest of the Simplis team, I would like to thank you very much for your time today. Cheers.